Thanks a lot for the kind introduction, and I'm pleased to see so many people here this evening interested in new technologies. My passion is about new technology, especially to retrofit existing production plants. That's something we need in Germany, but even more here in New Zealand. I know there are fancy solutions out there from Bosch, Siemens, ABB. However, a lot of New Zealand companies can't afford that. So I would like to show you today two examples how a technology can be used to improve productivity. The keyword is digital twins. It's a technology related to Industry 4.0. So first of all, I want to show you what is a digital twin and show you two applications. One from Germany in a steel mill, the other one here from New Zealand from wood processing. However, the concepts are not fixed to these production sites. It's a quite flexible approach. I just use these examples to make it a bit more tangible. What is it and how is the concept of decentralized production planning and optimization working? Here I would like to distinguish what is a digital shadow. This is more or less state of the art. You store all your process information in a database in time series. So that's good. A digital twin has got also access to this data, but is doing something more. And we talk today what this more is. So we've got access to all this data, we've got access to models. And you may say, oh, we're doing simulation and modeling since decades. That's true, me too. The new thing about the digital twin is that it connects real-time sensor data about your production plant, your products, and that makes your model, your simulation alive, and then we call it a digital twin. When it represents something, a physical asset in the real world, in real time, fed by sensor data, then we distinguish between a simulation model and a digital twin. So our digital twins, we combine that with agent technology, a well-proven approach of IT. An agent is a piece of software. It knows who it is. It's got a kind of identification. It's got some communication capabilities. It can communicate to other agents. It can receive messages. And within some limitations, it's got a reasonable understanding. That's more or less rule-based. It's not really intelligent, but it receives messages. It knows what to do. It's got some rules how to react on that. It can negotiate autonomously on markets between other agents, for example. And it's got access to its memory and its access to data. So we switch that passive digital twin to something active. And how does that look in a steel mill? You've got tons of data, for example, for flat products. You've got surface inspection data, all the defects. You've got thickness over the length. You've got flatness profiles. A lot of data stored to your product along the length. Digital twins of production sites are more or less well established and state of the art. So that's a simulation model with live data of your machine. A digital twin of the product, that's still under development a bit. First implementations are done. So we are simulating properties of the product. And why is that useful? For me, it's about the problem to improve production processes. So, and then I'm looking for the right technology to do that. However, in that case, they modernized the hot strip mill, the German steel mill, and then the next processing stage, the pickling line, became the bottleneck. So the manager of the pickling line called me, hey, Jan, CEO is calling me all the time. I'm now really under pressure. I have to do something. So we made a brainstorming session together with their engineers. What would improve that process? How could that process work faster? And we decided if we want to improve that process, just to those of you who are not familiar with that, during the hot rolling, you reheat a slab, roll it down to maybe 4 millimeters, and then it's leaving that process with 650 degrees in a coil. And because the surface is so hot, there is scale, a kind of rust growing on that surface, which has to be removed before it further can reduce in thickness in the cold rolling process. That's where it's coming into a pickling line. These are acid tanks where you, in a continuous way, transport your strips through these acid tanks, and that scale is removed. So to improve that process, these coils should arrive warm instead of cold. Usually they are immediately cooled down to room temperature or outside temperature, very cold in winter in Germany. And then these acid tanks have got almost 90 degrees and has to be reheated again. So that slows down the process. it would be faster if they arrive warm. So we decided, okay, to make that happen, we need some models, we need some decentralized optimization because it's hard to predict how the weather is and how the production will run in a week. So the centralized approach wasn't working properly. What we've done, we first had to solve a gap in tracking and tracing. I mentioned that already in the lab, installed a camera, reading the number of the coil transported by the floor transportation, and now the timestamp when that coil will transport it into the coil shower. That's the moment when our digital twin of that coil is born. The reason why we introduced that virtual copy of that is the coil itself is dumb. It can't do any communication and any optimization. So that digital twin starts a communication with the pickling line. There's also a digital twin running, and asking him, when are you going to process me? It's got also models inside doing a calculation that in 18 hours I would like to process you. Our digital twin now is okay, at the moment I've got 650 degrees, and in 18 hours I would like to have maximum 80 degrees, but close to that. It looks outside to the temperature sensor, we've got 10 degrees. We've got some feedback here all the time. So we're using these models to calculate what would be best water cooling time, and what, because remaining time at air is 10 degrees. So instead of the usual 8 hours, it may use only 5 hours of water cooling because there are 13 hours air cooling afterwards, arriving perfectly in the right temperature. So here's a kind of paradigm change. Usually the machine.
2 mics for you? Or?
Yeah, they asked me to use 2 mics.
One is for the audio for the live stream.
Yeah.
So it's not interfering with the other one.
Okay.
Thanks for asking.
Yeah. So the paradigm change is that usually the machine knows best how to process that piece which is arriving. And now we have got a virtual copy of that product telling the fine-tuning to the machine. So that virtual digital twin is telling the coil shower, put me in a row where I get only 5-hour water cooling instead of the standard 8 hours. The effect is the coil arrives warm, and again, we know the temperature. And again, a cold coil would have processed slower. So now the digital twin is telling the pickling line, here in the beginning, I've got maybe 75 degrees. That means you can process me maybe 20 minutes per meter faster. In the middle, even a little bit more. In the end, a little bit less. So again, the digital twin is telling the fine-tuning to the machine. And we're using models. The temperature model for the cooling with water and with the air. We've got another model modeling the scale growth, because it's quite deciding part if it's taking 20 minutes or 60 minutes before the coil shower starts. And again, then this model tells the pickling line, is it hard to pickle? Is there a lot of scale on the surface or not? Information which haven't been available to the operator before. And these are the effects. What does it mean for production? First of all, we implemented that, and we see in the top graph the change of the temperature. The black lines are the normal temperatures of the coils, and the red lines are the coils produced with a new regime. And the effect had been that we've been able to produce these products 16% faster. In the other steel grade, even 20% faster. And that by itself is a big number, but it's even more impressive if you think we haven't changed the pickling process itself at all. We just took care that the material arrives in a more suitable condition to the same process. But though these have been kind of expected or hoped effects, for sure you save a lot of energy, because a coil with 12 tons doesn't have to be heated up from maybe 0 degree outside temperature to 90 degree if it arrives with 80 degrees. But there have been also unexpected positive effects. Steel, which is 80 degree warm, is much smoother. They have some nasty steel grades which tend to break if they've got damages in the edges. And they've got in Parsitech a surface inspection system in the end, and detected, oh, we've got severe damages in the edges, and this strip didn't break. Meaning with every avoided strip break, you get 3 to 4 hours production time for free. And that is a kind of unexpected success of the process, which makes them quite happy. Okay, let's jump to New Zealand. We applied the same process and same product idea to wood cutting. It's a final year project running last year. Right now it's from Lizzie and Yiteng. So SQL uses 2 digital twin approaches, one for the product itself, and so They measure the log in 3D. They've got a lot of customized wood cutting, so all these orders have got different dimensions. The question is how to place these orders best in the existing raw material. So they have the digital twin approach for that. And they've got a digital twin for the sorting line. The process is you're cutting your boards. They've got all different dimensions, and now you have to sort them. Because you have to deliver stacks of certain dimensions, but from one log you get maybe 8 different boards in different dimensions. So they've got a sorting process, and that means you've got 18 bins. And up to now there was a manual decision which bin has to be sent to the stacker afterwards. And it happened quite often that the whole process had to stop if the bins are full, because if you can't put anything to that sorting line, you have to stop sawing boards. So the idea is we develop a digital twin for that stacking process. Ah, it's a robot. Hello.
Cheeky robot trying to get in on the action.
Yeah. Good guy, yeah? All good? So we've got now a digital twin of the process, receiving the information of the product, what is coming. So it's looking into the future, what are the boards arriving next hours, having models for the stacking process, how long would it take, and is able now to make the decisions with discrete optimization, which sequence of emptying these bins would be the most efficient one. Something which a very good operator with a lot of experience also can do. If it's not that experienced, the efficiency is not that high. So the computer model has got the ability to analyze much more configuration and possibilities than a human brain usually is capable to do. And so we simulated and estimated how big is the potential to improve that. And we saw one situation, the last line, where you see the emptying sequence, what the operators did, and result had been 10 minutes downtime. And we suggested, okay, if you would have used the other emptying sequence, which you see in the middle, you would have avoided that downtime totally. So the estimation is that if they implement that, there's a chance that they will increase revenue by 2.4%, meaning maybe $1 million per year. So that has been quite successful, and they are doing the on-site integration right now. They hired Lizzie, is now there at SQL, and I've got further projects with SQL together. So this is just one example what the outcome of a final year project with our university could be. Okay, that's from my side. Thanks a lot for your attention, and happy to answer questions.